Hello, welcome back to the channel. So in this video, we'll derive a new reduction formula, but this time for the integral tan to the power nx dx. So whenever you have an integral of the form tan to the power nx, you can always use this reduction formula in order to simplify your indefinite integral over here. And this also applies to definite integral. If you have a definite integral, you'll calculate the indefinite integral first and then plug in the endpoints in your indefinite integral, right? So now in this question, we have to prove this expression over here. We have to solve for the integral tan to the power nx so that it looks like this form over here on the right hand side over here. You remember we did a similar question for calculating the integral of sine to the power nx dx, which we solved using integration by parts, but in this case we'll use substitution. In this integral over here, we'll use substitution and also one more trigonometric identity of secant square being equal to 1 plus tan square x, right? But now the main question is, why are we using substitution and not integration by parts in order to solve this integral? So the reason why we are not using integration by parts, because in integration by parts we generally need two functions, right? So if we need two functions over here, we'll have to split our tan to the power nx into two parts, just like we did in the case of sine to the power nx. But in the case of sine to the power nx, you had sine to the power n minus 1 times sine x, and you already knew the integral for sine x, right? But in this case, if we have to split our integral into two parts, tan to the power n minus 1 x times tan x, we'll have to know the integral of one of them, right? So that would be the first thing which will make your calculations a bit more complex. And even if you know the integral for tan x, which is log of secant x, if you'll use the first function as tan to the power n minus 1 x, the second function as tan x, and solve this integral by integration by parts, you'll see that you'll make your second integral even more complex than the original expression over here. So that is why we are not using integration by parts in order to evaluate this integral. We cannot use the normal methods as well because tan to the power nx is not a familiar function that we know the integral for, right? So the only option that is left is substitution to solve this integral over here. In order to use substitution, we know that we have to have the function and also the derivative present in that same expression over here, right? And now we know that the derivative of tan x is secant square x. So we need a secant square term over here with the dx so that we can use u equals tan x, and in place of secant square x dx we can write du in place of that. So now, since we know that in order to get secant square we need a tan square term, so we can easily split this integral as simply calculating the integral of tan to the power n minus 2x times tan square x dx over here, right? And we can use this identity to substitute the value of tan square x, which would be secant square x minus 1, right? So this would be tan to the power n minus 2x secant square x minus 1 dx over here, right? And now in order to solve for this integral, we can split both of these portions over here. So the first portion is tan to the power n minus 2 secant square x dx minus integral tan to the power n minus 2 dx over here, right? And in the original expression on the right hand side, we have a minus tan to the power n minus 2x integral, which we have over here. If we solve this one, we will get this expression over here. So let's solve this using substitution, because now we have tan x and we also have secant square x dx over here. So in order to solve for this indefinite integral over here, let's find this indefinite integral first. So integral tan to the power n minus 2x secant square x dx, we'll just assume our first function to be tan x. If we calculate the du in this case, it would simply be secant square x dx, right? And now let's do all the substitution which we have been doing in the previous videos as well. We'll use the same approach. So it would become u to the power n minus 2 du, and then this integral would be u to the power n minus 1 upon n minus 1. And here, since we have an indefinite integral, we'll add the constant of integration at the end as well. But in order to get the final answer, which should be in terms of x, we'll have to convert u back into tan x in order to get the final integral over here. So the final answer to this expression over here would be, if we substitute u equals tan x in this expression, our final answer would be tan to the power n minus 1x upon n minus 1 plus c over here, right? So now if we again go back to our original expression for tan to the power, for integral tan to the power nx dx, which we calculated as this one, we know the integral for this, and tan to the power n minus 2 dx is again of the similar form as tan to the power nx dx, right? So we can use again the same approach to calculate this integral and then keep on reducing the tan powers until we get a very simpler expression at the end. And now we can calculate the final answer to this expression as well, which would be equal to tan to the power n minus 1 x upon n minus 1 minus integral tan to the power n minus 2 dx as well, right? So now this would be your reduced formula for calculation of the integral of the form tan to the power nx dx. The reason why we didn't add a constant of integration over here, because we already have an indefinite integral. So when we'll solve this indefinite integral, we'll add the constant of integration at the end to account for the indefinite integral over here. So that's it for this video. Again, the main takeaway from this video is, in order to solve for the integral of tan to the power nx dx, the best approach that we can use is substitution instead of following the integration by parts approach, because if you follow the integration by parts approach, you'll make your indefinite integral a bit more complex than the original expression over here. And again, to solve it using substitution, we use this trigonometric identity over here. And when we use this trigonometric identity and then using substitution to calculate or simplify the indefinite integral, we got this expression over here. And the reason why it's called the reduction formula, because now your integral of tan to the power nx has been reduced to just calculating the integral of tan to the power n minus 2 dx, right? And you can keep on using the same formula again and again in order to simplify your indefinite integral and calculate the final answer. Don't worry, we'll do another problem in the next video which will help you understand what we have to do in order to calculate the integral of tan to the power nx type questions, and how we can use the reduction formula to reduce the powers of the tan function. So that's it for this video. Feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.